So we're starting a new topic today. Before we start the new topic, any questions about previous topics that we covered so far, the protein structure? Any questions, any concerns? I don't know if all of you attempted, but that would be a great, yeah. Okay, yeah.
It's just a question about the worksheets. Are we going to get them back for feedback or no?
You know how that goes from the analysis. I will look at them, make sure you put effort in them and give you a score. If you have a question next week, I can answer it. So I can bring I don't know if I have a key. I might have a key.
Okay.
I'll look. I probably have a key.
That would be nice.
I think so. I will look to see if I have a key, I'll post it. Otherwise, if you have any particular question, you're not certain of the answer, I can go over it in class. But do you have a copy of what you submitted?
No.
If you want to take a picture of what you submitted.
Sure.
Pass it. And then give it to me. All right. What's that?
I think I did take it.
Yeah. I will, somebody reminds me, send me an email, say, Pam, do you have a key? I will search and I will put the key. You want to know? Okay. But yeah, as you study, just write down questions and just, bring it up next week or the week after next, because next week I will be teaching via Zoom from Austria, but the week after next week, it will be recorded. So it's best to come next week with your questions. And then we'll go over those together. Okay. Let's see. Any questions still, Sharu?
So I was reading like the amino acid composition, and then I was reading like, okay, what are non-polar versus polar versus like, and I read like, so, and I was looking at like the questions in general. And I was confused, how do you say if like an amino acid does have a charge? Like it said glycine is hydrophobic, but it is considered neutral, like it's
Glycine is not hydrophobic.
no,
Glycine is hydrophilic. Glycine?
yeah.
What is it said? What did it say?
So it's like, when I was reading, it's like hydrophobic, but it's neutral, like. So I was
Hydrophobic. Is it hydrophilic? It's the smallest amino acid, it has R group of H. Okay, let's see. Where is my?
No, it is hydrophilic. But like, how do you, even if it's hydrophilic, how do you say it's like won't carry any charge?
Polar. Not every polar compound has a charge.
Okay.
It's a polar compound. It interacts with water via hydrogen bonding. It doesn't have to be carry a charge and interact with water.
Like so with the steel and everything, like so whatever, so whatever.
Polar, like how I here, so these are polar that are charged, but then you have polar that are not charged. So I think. No, these are hydrophobic. Right, so these are the polar not charged.
Okay.
Not charged meaning does not carry a charge in the arching.
Okay, and, okay, I'll just like get the question which I got confused.
The amino acid here at close to neutral at the where you have this negatively charged and this positively charged, it is you have net zero charge.
Okay.
So it doesn't carry an additional charge around neutral. So, however, it is hydrophilic still. doesn't have to carry a net positive or a net negative charge to be polar. Okay. The R group though is can add a charge, an additional charge, so at neutral or around neutral, lysine is positively charged. Yeah, so it is a polar that carries charge at neutral pH. Carries a net charge, a net charge. Okay?
Yeah.
Good, okay. You had a question?
Yeah, I was just saying that I have the worksheet on my laptop, I just printed and give you out.
Oh, okay, yeah, absolutely, no worries. I mean, you can keep turning in before the exam, you can still bring them in. But I won't be here. Give it to me before. Okay, so yeah, any question? Me.
So we learned about different interaction, right? And then different functional group can give you different interactions. So let's say like two amino acid, can they have more than one interaction?
Yeah, depending on their location, you know, on the protein itself, yeah. And what residues are close by.
Okay.
They can't have multiple, yeah.
Piggyback off of that, like, I thought I saw that. The cysteine that has like sulfide over it.
Mm.
Yeah, can it be actually H bond? Is that like something?
Yeah,
Yeah.
yes, it can, yeah, it can participate because S is electronegative, yeah. So the hydrogen bond is with the H bonded to an electronegative with an electronegative. Mass. Okay, more questions? You know, think of questions that you want to ask me next week during class in preparation. You know, the exam is coming up in a couple of weeks, so make sure you're comfortable with the material. Okay. And you don't want me to ask, if you don't want to ask in class, you can email me and ask me outside the class too, so that's fine. Okay. And I just want to, you know, let you know that sometimes when I cover a topic, I try to give you examples to show you the whole picture. But during the entire semester, I'll be covering those individual, you know, information. So we will be touching on things in more detail, but when I start a concept, I try to put it in a big picture for you. So don't get too overwhelmed. By the end of the semester, trust me, you'll be experts. Okay, so this is your favorite part. I'll tell you why. Because most of you is what you're doing in the lab with all of the protein structural characterization and analyses and all of that. But what this is gonna help is put some basics to what you're doing in class, in the lab. So for most of you, some of you are not familiar altogether, so it could be a good overview. However, I want to say that I do not go in details in principle that has been covered as an undergrad. So I'm not going to explain chromatography like I spent 4 or 5 lectures in food analysis talking about chromatography. Here, I'm just going to talk about it briefly and tell you how we use it. So if you have any like doubt about a method, you have to go back to your undergraduate classes and get that information, because we cannot spend a whole semester talking about this. So that's one thing. Another thing is I want to tell you that I put reading material for you on Canvas. So for example, you'll see a document like this. So I'm going to, you know, give you an example where we use MALDI. But if you want to know how MALDI works, this is here. I'm not going to ask you in an exam to tell me in detail how it works, but to have a kind of a general idea what MALDI does. I'm not going to ask you what matrix is used in MALDI, for example. I'm not going to ask you these things. I just want you to understand what information we can get from all. So there are other, like I talk about N-terminal sequencing, this is MALDI, but there is, a document for different, analytical tools we use that I have on Canvas, okay? All right. This is again, not to study and learn so that you're gonna be examined on, this is information for you if you want to know more about each of these methods. Okay. Let's see what you remember. Now, all of the above, absolutely. When you have protein in solution, we have different chromatographic tools and ways to separate them. These are only 3. We're going to talk about a couple others. But yeah, we can use chromatography based on the characteristic of the protein, based on what we know about the protein. We can separate it using chromatography. This you might not know as well, but what do you guess?
A and C.
A and C, any thoughts?
I was gonna say all of them.
What do you want to say, Sharu?
I think I will just say all of them.
All right, A, B.
Just
Just A. So N-terminal sequencing is a specific, also known as Edman sequencing, we're going to mention it. It is specifically determine the sequence of the amino acids in your protein. So that's structure information of the primary structure. ELISA and Western blot is not necessarily structural. These are immunoassays. So it gives you an information about the immunoreactivity of the protein. So it's just a function of the protein, not necessarily a structure. Of course, it is very specific to the structure of the protein, but it tells me nothing about structural information or data. Okay. So what's under protein analysis? There's so many things under protein analysis. So it doesn't, when we say protein analysis, it doesn't only mean quantification. Quantification is one portion of protein analysis. So to quantitate the amount of protein in your sample, that's one type of protein analysis. Another one, even you separating your protein, whether you're separating to produce an isolate or you're separating it for testing using chromatography or SES phage, you're separating the protein to observe it, to get data out of it, or you are purifying it. So that still falls under protein analysis. Characterization and identification. So looking at secondary structure, you're looking at tertiary structure, looking at surface hydrophobicity, using proteomics to identify this is all under protein analysis. Now, where do we need on this slide? Where do we need protein analysis? When we are producing ingredients, we want to quantitate our protein, we want to identify our protein, we need to characterize its structure. When we're doing basic research to understand differences about different sources of protein, for example, to functionalize proteins, and so on. For industrial applications, so I want to use protein in different food systems, I need to understand structure, how it's impacted by processing, so that I understand its application in different food systems. So I need protein analysis in all of that. So the methods, if I need to separate, isolate protein to produce ingredients, has to be legal, safe, economical. The protein has to have functional properties. we need to make sure that we have good nutrition. So basically, when we're thinking about our protein analysis, we need to determine the purpose, why we're doing this analysis, and if it is going to be used for food consumption, we think about safety, legal, economic for the industry, and nutritional implications. So that's why many of you know that we do all of the protein analysis, determine structure, function, nutrition applications. Okay, so review, so I'm not gonna spend a lot of time on this, but quantification, you are familiar with this, you have taken one time in your lives with analysis. So you know that we have different methods for protein quantification. The official methods of analysis are Calderon and Dumas. Both are based on nitrogen analysis. And we have, this is quality control, secondary structure can be calibrated by official methods of analysis. And then these are the research methods. You're very familiar with VCA, we do it a lot in our lab. Lots of labs use Bradford. We also quantitate using absorption at 280. So these are research methods because we want the protein to be in solution in some sort of a purified form. They are not useful for a food matrix that is complex. So complex food matrix, you need to use the official methods or IR that is calibrated using these methods. So again, we have research methods where they are quicker, gives us good results based on generation of standard curve, but we cannot have complex matrix because of interferences. For example, VCA is based on reducing power. So if you have high amount of reducing triggers, it's not good to use VCA. So every method has its own limitation, and that's why it is important that the proteins in solution in most purified form, and it's not meant to put a quantity. It's not for competitive between samples. So it's mostly you're comparing your proteins across different samples in your assay, not necessarily to say this has this much for sure protein count. Okay. Why do we measure? Nutrition label, very good. What else? Why do we care?
Maybe to determine the effect of processing or treatments.
Effect of processing, or if you're purifying the protein, you want to determine how much protein is in your purified sample. What else?
We also use it for the function now, yes.
Yes, we use it for functionality. Why?
Like we use that protein calculate or how many samples we need.
How many samples you need? I know what you want. I know what you want to say, but let's say I am. I want to run a gel, an electrophoresis gel, and I want to make sure I can compare my samples equally to each other.
You need to know the protein content because without that, like each of your samples will vary in protein content. So knowing your protein content, then you can weigh out your sample
Accordingly,
Yes.
and be able to compare functionality on a common ground. So when I load my protein on my gel, I want to make sure that every sample I prepared has constant protein concentration, so that when I look, well, this protein has a darker viscellin than this protein. Does it mean because I loaded more protein in this lane, or just because the sample has more viscellin or legumin in it than the other sample? So if I load only on protein content, then I can do comparative studies. Sometimes I determine functionality based on protein. Can you give me an example?
like multiplication capacity.
There you go, your favorite assay. So emulsification capacity is actually a measure of how much oil is emulsified by 1 gram of protein. So you have to know how much protein you have in your assay in order to determine that. If I am determining enzyme activity, I want to also know the units of activity per gram of enzyme or per gram of protein in enzymes, proteins. Okay, so. Yeah, I think we covered most of them. Quality control to determine that you have consistent protein if you're processing across your processing line. Usually use IR, mid-IR, or near-IR calibrated for fast measurements of consistent quality. Okay, so that's good. This table is FYI for you to kind of remember how each method is based off of. Again, what is most common, Keldal, nitrogen combustion measuring at 280. That is when you have your tyrosine and tryptophan, phenylalanine sometimes. This is peptide bond absorption. And then you have BCA we use a lot based on reducing power, Bradford binding to a dye. OPA, we don't necessarily use it to quantitate protein, but we could, but it's not used as such. And then you have other forms, but mostly you have your official methods, your absorbance, one of these research methods. So this just reminds you what the principle is, the sensitivity, issues with this method, and whether or not it's destructive. So those absorption, you can, for example, put your protein in solution, measure absorption, and use that solution for something else. So that is really nice here. And another non-destructive would be the IR, but yeah, not for here. I'm not gonna ask you principle. I'm not gonna ask you details to memorize, but I want you to have a general idea. Okay. We separate proteins sometimes. What's the purpose of that? Alyssa,
Sometimes it's good to understand like the functionality and structures of different types of protein in a livable protein. Like, for example, I can think like a very good example. So they're trying to make little proteins like casein whey from fermentation. So it's good to understand what each of them do.
absolutely. So you give a very nice example, more detailed answer that I was looking for. That's good. So you separate proteins sometimes to study them more, to understand them in a purified form, understand their structure. Sometimes if you want to get the sequence, not some, if you want to get the sequence of protein, really has to be in its pure form. You cannot take protein isolate and send it to N-terminal sequencing like that. You have to, it has to go through a lot of purification, sequential purification, and then a very pure subunit of the particular protein will be sent for N-terminal sequencing. So sometimes you just use protein separation in order to isolate a particular protein and know more about it. Okay, what else? So you want to think of separation and purification, not just.
I'm thinking if you want to make a product that is like only whey protein, for example, you have to separate your protein.
So an isolate, you want to produce a concentrate, you want to produce an isolate, you have to go through a process of taking that protein out of the original matrix. So if you have, separated from starch and fat and fiber, or in milk, you want to separate the protein, whey protein from casein, from fat, from lactose, and so on. What else?
To study, like, for example, in a sample, for example, hybridized, to study what all protein fractions are actually separated.
Absolutely. So let's say, the example that Sharu was talking about is hydrolyzed protein. We want to look at the peptides, and we want to understand the functionality of these peptides or the molecular characteristics of this peptide. Later on, I have an example from research we've done in the lab on that. So understanding a particular characteristics after certain modifications. Sometimes it's enzymatic hydrolysis. Sometimes it is you glycated and you want to separate that glycated protein and know where the location of glycation occurs. So where did that sugar bind? And how does that impact the structure? We had research back in 20 years ago on that. And I have examples to show you. What else?
There's enrichment,
Enrichment.
like what Holly did, and she gave 7 months ago.
Oh, yeah, I have that. I added this paragraph today to the presentation to this lecture. Yes, so when we want to purify compounds and then use them for as standards, for example, part of Holly's continuation work is to get those pure standards and use them to feed NIR instrument to detect ratio of viscillin to legumin in different varieties. So yeah, another, I think we're giving more examples than what I just, those headlines here. But if it's an enzyme, you purify the enzyme, it's a protein to use in enzymatic acid. Sometimes you purify substrates to use for enzyme analysis or activity assays. In fact, the processing, you guys do that for analysis of your samples, use size exclusion chromatography because you want to determine impact of thermal treatment on the formation of polymers. So you separate using size exclusion and determine the molecular weight distribution. So a lot of different reasons, and many of you are working already on that, but now we're putting things in perspective. Okay, so when we think about separating, isolating, purifying, whether it is separating the proteins from carbohydrates or separating individual proteins within a crude mixture of protein, we need to know characteristics of those proteins. And we want to use this knowledge, the characteristics of these proteins, to devise best way to separate them. So proteins differ in nutritional quality, they differ in functional properties, they differ in biochemical characteristics. This is what we focus on in order to devise protocols to separate, isolate, and so on. We look at how they are different in biochemical characteristics. And the biochemical characteristics, we talk about, okay, they differ in size, they differ in charge, at different pH and salt. They have different extraactivity to different matrices. They might have different affinities. They have different thermal stability. They have different solubilities. So these characteristics are governed, all of them are governed by your MS and sequence. So the composition and sequence dictate molecular structure. And also dictates all of those surface properties, solubility, here's the sequence, the composition and sequence determines how casein is different than beta-lactoglobulin. This is open structure, this is globular. We'll talk more about why they are that different in our daily protein. But the composition and sequence, we talked a little bit about having high proline concentration. At 18% proline, it's secondary structure breaker. You don't have beta sheet, alpha helix, and it's open structure, whereas beta-lactoglobulin has certainly a high amount of hydrophilic amino acids, some hydrophobicity, so the hydrophobic residues try to hide from water to form a nice globular with a structured secondary structure. So composition and sequence, you want to remember, dictates the structure, and that structure dictates how soluble the protein is, what are the surface properties of the protein, and also the size of the peptide determine how big that protein is going to be. And also the composition determines thermal stability, and so on. So the protein's different and all of that, so I utilize all this information to figure out how I'm going, oh, this is another form. The quaternary structure in plant protein, that they have a lot of surface hydrophobicity, so they associate to form quaternary structure. So I need to know all of this about my protein in order to devise ways to separate them. Okay. We're going to talk about all of these biochemical differences and how we utilize them to separate proteins. But stepping back, if I want to separate and purify protein, what do I consider as a first thing? You're starting with something and you want to get the protein out. What was one of the first considerations that many of you?
I guess you could think about the composition of the overall starting
Yes.
material, so that content comes to mind. and then
Absolutely.
What your proteins are soluble in, and then the salt.
That's it. That's good. So first thing, is there high fat? Do I want to remove the fat so that I can isolate my protein efficiently from the carbohydrate? So I think about the matrix of the food system that I want to get my protein out. Okay, very good. What other consideration?
That specific protein which is soluble in a particular solvent.
Yeah, yes, absolutely. But I'm thinking like broad. If I want to start with, I have a mission and I want to isolate my protein. Think about the matrix. Okay. Bigger level. What other than the matrix I want to think about? You are going very specific. This is all consideration, but before we go into that,
Would you wanna consider, what you wanna use that protein for, like if it's gonna be used for food application, or if it's gonna be used like.
okay, so you want to consider if your isolation is going to impact its functionality.
Yeah.
All right, thank you. Yeah, yeah. So how is my method going to impact how I'm going to use it later? Good, but there's another thing that is very important.
Pure, like.
Yes, how pure it is. I want to generate a concentrate? Do I want to generate an isolate? Do I want to really get one protein out? So yes, so these are considerations. Let me see. Oh, there's one more. If I'm in industry, what would I think about? Money. Okay, so nature of the food matrix. How much pure and what quantity? That is heart aching for Holly. How many extractions did she have to make to generate all these little fractions? So how much do I want to produce? And then what's the degree of purity I want? Stability, what is it going to be used for? How much do I care about that? And cost. Okay, so how do I monitor effectiveness of my method?
I have a question before you go on to effectiveness.
Yeah.
Are all the like extraction or separation and purification methods that we use in lab, like food grade, like can they scale up and they're all okay to use?
So good question. So is everything we do in the lab food grade? Well, it depends on the purpose we're doing in the lab. For example, when we use alkaline extraction or salt extraction to get an isolate, yes, we scale it up. So we think about NaOH, I can get a food grade NaOH. NaCl, I can get a food grade NaCl. So if I'm after producing an ingredient, so definitely I want to consider what I'm using and if it can be scalable for food grade. But if I'm doing this to get a pure protein just to characterize for structure, I don't care if it's food grade or not. So yeah, for example, I give again the example of Holly. She took the pink flour and fractionated those proteins into a different fractions. We use a lot of reagents. We don't care about food grade in this case. All I care is getting a very pure fraction of that pink protein. Okay, good.
Yeah, like we usually check the actual moisture content
Mhm.
after, for that protein isolate, we want to make sure there's low salt.
Salt.
And I also want to make sure it's the free dryers. Okay, like if it's dry, no. The
If
sample
it's
is
dry, yeah.
like.
Yes, yeah, of course, you do compositional analysis, for many reasons, not just for purity, but like you said, the salt, what does it impact? It impacts functionality. Right, I don't want a lot of salt in there, it's gonna impact the protein functionality, but also salt impact the method, if I wanna do LCMS/MS, there is a desalting step. So if I am separating my proteins using seismic protein chromatography, like Coleman's gonna do for his gluten proteins. Gonna separate them, but before he takes them for counting center, he needs to desalt them. Because those samples have to be desalted before further analysis. So yeah, so the degree of purity and the composition of your final sample impact what you want to do with it next. Fat contents, we don't want high fat content in your protein ingredient because it's going to oxidize and then the protein is going to get the bad reputation of it tastes bad. It's not the poor protein fault, it's what comes with it. So, yeah, okay, so to monitor effectiveness, what do we do? Yield. So, the yield is heartbreaking for many of us. Yeah, so how much protein I was able to get out of my original sample? If I have 100 grams of pea flour, I have 20 grams of protein. That's the protein content of pea flour, about 20%. When I extract, I might not get 20 grams of protein from my 100 grams of protein. I might get 100, I might get 10 or 50 grams. So then my yield is 50 to 60, 70%. That's in very good case scenarios. But then we have sometimes, ask Abby working with oats, you get, or Andressa, you get 1% yield. Isn't that sad? That was like heartbreaking. And Rissa comes to me, I can barely see the packet. But it's not directly from oat flour, it's from a byproduct of oatmeal production. So oat flour is better, right? And Abby, like we get 30, 40%. Yeah, oh, yeah.
I didn't know that there's something worse than corn.
There you go. You go have a glass of wine with Andressa. Okay, so yield. What other than yield determines your effectiveness? Yes, Anastasia. Oh yes, oh my gosh. Yes, how long does it take you? 4 days, 5 days, or 1 day? That's great. Well, effectiveness, efficiency, I would call it. I don't have it here listed, but how efficient is your method? That's another story. Okay, so what else?
I think the amount of water,
What's that?
amount of reagent or water used.
Yeah, so we're talking about efficiency of the process itself. But how do I, after I get the isolation, how do I determine that it was good?
Purity.
Purity, yes, absolutely. So we talk about yield, we talk about purity. What else is important for us that we always mention?
Oh, yeah, functionality.
Structure, functionality. What did we do to the protein? Did we do it, kill it? Is it still functional? If it's an enzyme, does it still have activity? Yeah, so depending on what is our purpose, we can determine the effectiveness. Quantity, there is purity, yield, structure, functionality, or activity in case of. Okay, so this is effectiveness, but also this is effectiveness of the process to get your purification that you want. But you guys talked about cost and reagent. This is efficiency. Time, cost, reagent. This is how efficient that process is. That is a little different than effectiveness.
Excuse me,
Yeah.
and we also talk about the scalability.
Scalability, absolutely. You know, it's really here. Because when you are developing an isolation process for a protein ingredient, that's a consideration. How much does it cost? Is it feasible? Do you use a lot of steps that will make it not feasible for industry? So that's under consideration. So before you start, can you scale this? Okay. So we're gonna talk about, and most of you already do these things, is that first of all, you extract. Meaning, what do you do the first step? You have a matrix. If it's defatted, what do you do next? What do you try to do? You solubilize the protein. So you want to solubilize the protein and take out not the other components that cannot be soluble in your matrix. So you don't want fiber. So you solubilize the protein in hopefully water. Sometimes you need more than that to get that protein from water and from fiber and starch. So that's kind of like one of the very first things we do. Of course, there are pre-treatments. When we talk about pre-treatment, the pre-treatment includes dehulling, it includes milling if it doesn't have fat, it will include if it's soy, you dehull, you plate, you press, you do mixing extraction, then you get to the flour, and then you get to cellulizing the protein. So I'm not talking in this table about pre-treatment before you get to the cellulization stuff. And then you solubilize the protein, but you have other things that are going to be in your soluble protein. So you want to separate, so you can precipitate or do membrane separation. So that's what we do in the lab, is that you solubilize first and then purify further by separating the protein from other solubles. Sometimes you can use ultracentrifugation. This is common for, actually I did that when I was a postdoc, trying to separate casein from whey protein from milk. I didn't want to use curd, I don't want to generate curd and whey, just take the milk, you do ultracentrifugation, you get the fat. Well, first of all, you do centrifugation, you get fat out, and you take the liquid, you put it under ultracentrifugation, you separate casein from whey protein. Chromatography, of course, we're gonna talk about a lot of examples that involve chromatography. This can be done on a lab scale to purify and characterize, understand molecular distribution and all of that, but also it can be done on industrial scale. So Agripur, who used to be the Visco before being Agripur, they had a patent for the longest time to produce the whey protein isolate using ion exchange chromatography. And they had the best solubility in terms of the whey protein ingredient compared to whey protein produced by membrane filtration. So chromatography can be done on a small scale for analytical purposes. Here's your wonderful, you're gonna spend lots of months on that. Okay, so you can use it for analytical purposes, small scale purposes, but also large scale industrial purposes for separation. Okay. Break? All right, break till 55. So 7 minutes.
Today we recording. I think the lot of people was also from the DC located. Yeah. In my email, you may see that they took the air, compressed air thing from the units, and then later the font air to put it back with Igor. But Igor told me, I think JP took the water freezer to replace the new one. And then I asked, is it very important? And then Igor told me, yeah, if we are going to do the olfactory, it is necessary to moisten the air. Why did they take it? I emailed JP to confirm everything, to make sure. That's why I decided to cancel the training tomorrow. And also, as I said, CIS unit yesterday we tried, it didn't work. And this night they will come and tell you. Respond to your lab. No one. just only one. Coleman told me he had made 3 new traps. Because last summer before I leave, I gave all the traps with me to Leslie for her study. And Leslie gave the 3 new ones to Coleman.
So he has.
3 new ones we had at least. So we have enough traps. But the other, traps which are broken, no one didn't reply me back. I also talked to Devon about it. Devon told me none of the person from Gary's lab is working after that. But I tried to purchase adapters, of course, we have to have. I couldn't find exactly that pieces. I think it is not producible, I am not sure. Because it is. Okay, because I tried, I couldn't find from New Market or the.
Yeah, tell JP what we want exactly, he has his sources.
Okay, okay. Then, I am trying to get all pieces together, once everything seems ready, and we are. Also CIS unit was not responding yesterday. They will check this night, and then he will let me know what is the issue. It is better with the nitrogen, or he told me sometimes software is not responding as well. So, yeah, this station.
I think.
I didn't see something, yeah, I didn't spend so much time. But all the things are changed.
I think it would be good to connect with Leslie one-on-one, just to understand from her what happened with the last person.
Okay.
I think he has an idea of what things when.
Yeah, I can ask for it.
Yeah.
Mhm.
Just one,
And then we
one,
can.
don't copy. That information. Yeah.
And then, let's say, if Jacob told me he was filtered from the Lect unit, then, basically, olfactory won't be very strong, I believe, at the ultimate.
We just need to get what we need to get.
Okay, then I am going to let him know if it is taken, and then I can ask him to get the pieces and then.
Yeah.
Put it back.
Consult, when you talk to JP, copy Karthik and Chris,
Oh,
because
and-
they were in communication for me.
For the GC.
For the building staff.
Okay.
So that you get the whole story, you wanna check with Chris, maybe you know.
Oh,
What
okay,
happened.
yeah, that before not getting all the pieces together, I shouldn't do that, right?
We'll get more problems.
Okay, that is good to know, because I was thinking maybe we may do next week, but I think it is better to get all the pieces together.
To understand the
Mhm.
impact.
Okay, okay.
One question. It seems license is non-polar. I think that's what I was getting confused with, because I read it.
Yeah, there is this Christmas.
Oh, okay. So we do consider the hydrophilic node.
Oh, yes.
Yeah. Oh, that's why we found it. Actually, I read it.
Yeah.
Yes. Yeah, so we want to make sure that it's lower than 8% before we mill. Yeah, and then we want to make sure that it's lower than 8% before we are constructing. Yeah.
Yeah, the 8% is because out of the trials in the past, we found that the building costs, I know, you cannot run like the.
Okay.
That's why we determined it has to. But for that, gonna be the lowest possible, because protein. And then it will be hard.
So I would. It's like I need to the writing on. Yeah.
Yeah, that's what Laura did.
I know. It's pretty grand. Yeah. It's the same, but I'm just wondering, after the diversity, still, like, the fact that it's still higher than.
Well, she example that he that really is important.
Okay.
And, but she, but the cycle, two cycles, she has
Okay, so this is like going to be the, where I was, like, if just like it's not enough, I'll do it.
Yeah.
So, those are first, yeah.
Well, because you need to. Now, I don't know.
That life, oh yeah. It's like there's. Yeah, no.
All right, let's get back. Come back. Okay. All right, so we're gonna talk about different isolation approaches and then the chemistry behind them. So some of you are familiar a little bit with this because of the work we do in our lab. So we have, when we produce an ingredient, two common processes we call dry milling and wet milling. So the dry milling usually gives you, and that's in the plant protein world. I'll show you examples for the milk, for example, world, different than this. But in the plant protein world, when you start, let's say, with a pulse, you have a lot of fiber, starch, and protein. Air classification separates by density, particle density. So you can have the light fraction and the high density fraction. And then the light fraction has the higher protein content. And it will usually get you a fraction that has about 50 to 60 percent protein. So we call that protein concentrate. That's in the pulses world. And in the pulses, we can also do wet milling. I'll talk about that as well. But in, let's say, oil seeds, we don't do usually air classification to produce protein concentrate and isolate. It's always wet milling for oil seeds, but for pulses, you have these two options to produce a concentrate and an isolate. So this is air classification, which is based on the density of the particles. So you end up with a high starch fiber fraction and a high protein fraction. The wet milling is usually most commonly in industry we use for plant proteins alkaline pH extraction, because most of your plant proteins have higher solubility above pH 7. Because you have all of these ionizable group at alkaline, like tyrosine, for example, is ionized SH. Sulfide groups are ionized at alkaline pH, so it enhances the net negative charge. So you get protein soluble above pH 7. So that again, depending on the composition of the protein. And what we do after we solubilize, we bring the pH down to the isoelectric point. to separate the protein from other solubles, from soluble fiber and soluble small sugars. Monosaccharide, disaccharide, and oligosaccharides. So, and then after we isolate, we neutralize, dissolve, and spray dry. But then we base our separation and purification on this kind of pH solubility curve. The other process is using salt. So we solubilize the protein by at a certain salt concentration to enhance a phenomena called salting in. And again, I'll explain more in detail later the difference between salting in. Now, so salting in is basically you increase the charge load on the protein. So the salt is interacting with the ionizable groups of the protein, and then you're increasing the charge load where water can interact with those charges on the surface of the protein to enhance water protein interaction, so you get the protein solubilized. And then you do the centrifugation, you separate everything that is not soluble, and then you have your soluble protein in solution with other solubles. To separate that protein, you use a salting out, meaning you increase a lot the salt concentration. And instead of adding, the salt will have the opposite effect. It's still interacting with the protein charges on the surface, but now it's not really increasing the charge load. It's basically shielding the charges on the protein, neutralizing, shielding the charges on the protein, and then reduces protein water interaction, and also compete for water with the protein. So you have a lot of salt, now the salt won't interact with water. It's shielding those charges on your protein gets released. And then you get your protein to be very, very high in salt, and then you do washes and, to remove the salt. But that is not economical in industry, because then you will use a lot of water that's not efficient, and then you will have a lot of water salt waste. So what we do in our lab is we do the membrane filtration. Membrane filtration at cost, obviously, but it is definitely more efficient, and it is used in industry. So we do membrane filtration to produce other types of ingredients like whey protein isolate concentrate. So in this system, you are basically concentrating the protein by retaining it on the membrane, and then your salt, sugar, and also you concentrate for diafiltration. Salt, sugar, water go through the membrane, you concentrate your protein. So let's step back a little bit and talk about the chemistry behind it. So what happens at the isoelectric point? Your net charge of the protein becomes zero. That doesn't mean you have zero charge. You don't have zero charge. You have net zero charge. You have charges on the protein, but they cancel each other. At that point, when you don't have a net charge, the protein molecules no longer repel each other. You don't have net negative like in the case of casein and pH7. You have net negative and net negative, they repel each other, they stay in solution. You bring down the pH to 4.6 for casein, it's 4.6. Now you have neutral charge, so now these caseins are no longer, or these proteins, whatever it is at the isoelectric point, you don't have any more repulsion. You have hydrophobic attraction. So no repulsion, you have hydrophobic attraction, and then the protein aggregate and precipitate. Yep. So that's what happens. I kind of explained before showing. Now salting out we talked about that high concentration of salt, the solubility of the protein will decrease. So here's your salt ions, they shield the charges and compete for water, compete with protein for water. A very common salt used for salting out in industry, or we have used it as well, like we use it for hydrophobic interaction photography, is the ammonium sulfate. So at high concentration of these ammonium sulfate, we're shielding the charges and competing for water, causing aggregation and precipitation. Here's a question for you. I have a mixture of proteins, and you always have a mixture of proteins. There's like tons and tons of proteins in different sources. All right, let's make it simple. We have 5 different proteins, A, B, C, D, E. A has the least charge, B has the highest net charge at a particular pH. I want to isolate C. Think in a simple way, how would I approach taking the middle here that has in the middle of the charge? What would be my approach, Yes.
So, what comes into the top of my head is, first you salt out A, B, centrifuge that out. And then you salt
A, B, and D.
No, A and B,
A and B.
you centrifuge to
Yeah.
separate, and then you salt out C.
Very good. So how do I do that? I need to know A, B, C, D, E very well. I need to know at what salt concentration A and B will precipitate. So I need to know some physicochemical information about my protein, but the idea, as I said, is I will add a little bit of salt that I ensure A and B will just fall off because they have less charge. The less concentration of salt will shield that charge. And when I centrifuge, these will precipitate. Then C, D, and E will remain in solution. I increase my salt concentration just enough to precipitate C and keep D in solution. So I'll show you later on, like a very tedious separation for an enzyme inhibitor from milk. How it's tedious, you would change the salt, change the pH, multiple steps until you get to that very pure protein you're after. Solvent fractionation. Sometimes you also use alcohol or organic solvent to precipitate the protein. How does that work? Is when your protein is in water and then you replace the water with alcohol. What happens is the protein, why does it take a globular, let's say the plant protein shape? It's hiding its hydrophobic components from water. If you take water away and put organic solvent, now the protein is going to say, oh, I like that. I'm going to open up and have my hydrophobic interior interact with the solvent. So now instead of having water protein interaction, I would have solvent protein interaction and hydrophobic driven interactions, protein interactions, and then they aggregate and precipitate. Okay, denaturation. We can form protein aggregate just by heating and precipitating the protein, and just having a protein that is not very functional, but is potentially used as a nutritional supplement. So you can precipitate by heating, but we don't usually want to do that because oftentimes you want the protein not to be aggregated and denatured, and sometimes aggregation is irreversible, especially if you have disulfide linkages. You don't want that to happen, but aggregation and precipitation can also happen when you heat to the above denaturation step as well. Okay. Different protein will denature at different temperatures. So knowing the protein and knowing at what temperature to use to cause denaturation and precipitation is important. And here's just two examples, very different proteins, both from milk. One denature at 73 and another denature not until 140 degrees Celsius. That's because of how one thing that will come back to us when I cover denaturation, thermal denaturation, I will mention again that the more structure you have, the more you have ordered structure, the lower is your denaturation temperature. So the more you have like alpha needs beta sheet, this is order structure, you would need less temperature to denature. The less ordered structure you have, the higher is the temperature of nature. It's already not ordered. So it's already open structure. So it takes a lot of high temperature to kind of even change that structure even more. But we have a whole section on denaturation later on.
Yeah, just to clarify, for this method, so let's say we wanted casein, then we could denature our way, like go past.
Yeah.
73,
Yes.
And then we'd be left with our casein.
Yes, you can do that.
Okay.
Good. Now, this is example that in industry, this is how they produce soy protein isolate or soy protein concentrate. So again, there's this pre-treatment that gets you to defatted soy flakes or soy flour. So that is the dehulling, the tempering, flaking, pressing, solvent extraction, you get to defatted soy flakes, and if they mill it into flour, will be even better for protein extraction. You don't want to start with the defatted soy flakes without milling. You have the alkaline protein extraction, the most common. So what they do is you solubilize, usually in industry, anywhere between 8.5 to 9.5. If they solubilize at 7.5, it is good, but to enhance yield, they increase the pH. So they solubilize the protein, they centrifuge, separate from fiber, then you have a protein solution. They acidify to 4.5. They precipitate the protein, separate from solubles, oligosaccharides, and soluble fiber. Then several washes, and then neutralization. You always want to neutralize. You don't want to dry and isolate. Okay? You neutralize, you spray dry, you get soy isolate above 90%. The other side is if I solubilize with aqueous alcohol, I solubilize all of my sugars, monodioligosaccharides. And even if I solubilize with just a little bit of water, but mostly you want aqueous alcohols. You don't want to lose any of the water-soluble proteins. So then you separate, your precipitate in this case is your fiber and protein. That's why you have a concentrate here, because you have a high concentration of fiber in this case. And very commonly, this is used to generate texturized vegetable protein, low moisture texturization. Okay, now there is another way of getting a concentrate that I don't have here. Usually they solubilize or they put in water and they acidify right away. So if you put in water and acidify, your protein and fiber will precipitate and solubles will remain in water. So they acidify and then you neutralize, the spray dry, you get the concentrate. More commonly than not, because a lot of industry or plants, they don't want to use alcohol. They do the acid precipitation right away here. So they skip the alkaline solubilization and go directly to disperse in water, acidify, precipitate, dry, and you get your soy concentrate. Okay. So, like I said, this using chromatography, you can do for a lab scale and for industry scale. And you have different types of chromatography. The one that is based on absorption. Again, I'm not gonna go a lot into detail here, but one of the common absorptive chromatography is ion exchange. So, and that is the technology that Agripur had patents for 20 years. So you can use anion exchange or cation exchange. Basically, your most charged on the surface protein will interact the most with your stationary phase, and those that carry less charge will elute. And then to let that protein of interest leave the column, you change the pH, you change the salt, and you disrupt this interaction and you collect the protein. You can do low pressure chromatography, that's what mostly translatable to industry, or you can do high performance for analytical purposes. So you would use a high performance analytical column to separate the protein for analytical purpose. The stationary phase is for protein because the large molecule is polysaccharide phase. And then the OH groups are derivatized into either and cation exchanger, that means has net negative charge, so positively charged proteins are interacting, or they are anion exchanger with a positive charge, where your negatively charged proteins are being separated. The other form of chromatographic absorption is your hydrophobic interaction chromatography, which is very commonly used in the protein world because it's based on hydrophobic interaction between the surface of the protein, the hydrophobic surface of the protein, and the hydrophobic residues on the stationary phase. So what we do in this case, we solubilize our protein in high salt. So now the salt is shielding the charges on the protein. So when I inject on the column, the protein interacts via hydrophobic interactions with the functional groups on the column. And then everything that doesn't have a surface hydrophobicity will elute. So we use it, for example, a lot to separate, let's say, carbohydrate from protein. So when we're running with salt, your carbohydrates and small sugars, they would not interact with your column, and the protein will interact with the column. I gradually decrease salt concentration until I have 100% water, then my protein comes out, because now I have charges and then no longer the protein is interacting with the column. I can switch directly from salt to water, then I'm getting all my protein separated from everything else. Or I can gradually decrease the salt concentration, I can separate my proteins based on their hydrophobicity. So it really depends on how I want to use this form of chromatography. Affinity chromatography is used to purify a very specific protein, so it's very much used in immunochromatography, where we are isolating antibodies to be used as reagents in immunoassays. So that is very common. It's also used to purify enzymes. It can also be used to purify certain glycoproteins. So it has very, very specific use, and it's based on a very strong or not strong, very unique interaction or specific interaction between the protein and the ligand on the stationary phase. So it's kind of like how the enzyme interacts with the substrate. So it's a key lock. So it's basically very, very specific interactions. So it's very selective And that's why it's used for very unique purposes of purification. And when you have a mixture and you are after one particular protein, then everything else will elute, and that one particular protein will interact to let it leave the stationary phase in a reasonable amount of time. You change the conditions of your mobile phase, either pH or salt, or you add ligand that is similar to what's in your stationary phase to the mobile phase. So then you will have your compound move with the stationary phase. Okay, so I spent 4 or 5 lectures in analysis covering this. So this is just an overview to tell you how we use them in the protein world. But definitely go back if you don't know chromatography or don't remember chromatography. Figure it out. You can ask me, but you want to remember. So other than absorption, we can separate based on size. So one common tool we use quite a bit is when we have our protein that let's say we precipitated our protein using salt, or we solubilize our protein using salt, or we extracted our protein and we change the pH up and down and we generate a lot of salt. So common thing you do in the lab is you want to remove that salt. And what you would do, and you all mostly are familiar with that, is you would use dialysis tubing with specific molecular weight cutout. That tubing will have 4 sizes. You can select based on the type of and size of protein and the size of molecules you want to separate from the protein. And then you put it in that tubing and you put it in water mostly. So what happens, it's based on equilibrium. Over time, your salt will go out and then it will equilibrate. Inside will be equal to outside. So that's why it gets really important to change your water.
I'm just wondering, for the industry scale, if they apply dialysis?
No, they do diafiltration.
Okay.
Yeah. So you just they run the protein with a lot of water, and they do better than dialysis. They measure total solids.
The reason I'm asking at the end for the commercial ingredients, protein isolate, they are still too salty. So I was just wondering.
Yeah, because they don't do enough diafiltration.
Okay.
Sometimes they skip the whole membrane and then they just wash with water and skip membrane filtration to save money. Yeah. So, but yeah, so this is not the industry. So this is in lab when we want to remove our salt. We do that, and then that's why oftentimes I tell you it's not about how much water you put or how much you have in your tube as much as how many times you change your water. Because you're gonna reach equilibrium no matter how long you keep it in. If you just keep it 4 hours, you reach equilibrium. What's more important is depending on how much salt you have, that means how many times you're gonna change that water. The more you change it, the less the concentration of salt is gonna be in your finer protein. So here we have that to use to purify the protein from small molecular weight components, usually salts and sugars. Often your membrane has a layer of polyethylene glycol to prevent water going in the membrane and then bulging and getting like this coming to, I don't know, have more water in there than you actually put to start with. To prevent moisture migration, basically. We have our membrane filtration. So we have those small tubes where we can utilize centrifugation coupled with membrane filtration. And you can buy different tubes. This is one form of tube where you have a membrane here with a specific pore size. It can be like that, or it can be like in this picture. So what happens is you put your solution and then you apply centrifugal force, so you put it in the centrifuge. And then here you have a membrane with specific cutoff. So it can be 1 kilodalton, can be 3 kilodalton, can be 40 kilodalton, depending on what you want to separate. And after centrifugation, you can do multiple washes to make sure that, you don't have blockage of the membrane pores. And then inside here, you have the permeates. Sometimes you want the permeates, you collect the permeates. Sometimes you want what's retentate. Depending if if I have a protein hydrolysate, I want everything under 3 kilodalton and I want to dispose of anything above 3 kilodalton, then I care about that lower portion, the permeate. Scaling our protein production in the lab, some of you are familiar with this unit, where you have membrane filtration, where your solution is pumped into the membranes, and then also you use membranes as specific cutoffs, and then you have water washes, you get the permeates, and then you get your retentate circulated back. And then depending on the washes, the more washes you do, the less salt you get, and then also you concentrate your retentate. Now on an industrial scale, you can do that as well, membrane filtration, where you have your protein solution going in and then permeates. You don't want the permeates and you want your protein to be concentrated, as well as you want to reduce the amounts of soluble salt and sugar. Now the membranes, you can either have microfiltration, ultrafiltration, nanofiltration, or reverse osmosis. And it's used for different purposes. And common example, I use milk, for example, system to show the differences in molecular size and what type of membrane you use to separate the different sizes. So microfiltration, ultrafiltration, nanofiltration, reverse osmosis. Obviously, with reverse osmosis, you are separating ions, whereas, let's say, with microfiltration, you are separating fat globules, for example. So here is a diagram. So with microfiltration, let's say we have a milk system, fat and bacteria, and then protein, lactose, minerals, water go through. And then if I want to collect the protein, I would have the ultrafiltration system. Also, it varies. You have different pore sizes for different molecular weight. So you have a specific range for the molecular weight, and you retain protein, lactose, minerals, water pass through. You go to nanofiltration, you retain lactose, and then minerals and water pass through. Reverse osmosis, then you purify the water, and then the minerals go through. So I like that very much, using the milk system to differentiate. But now here's an example of using membrane filtration to generate whey protein concentrate, whey protein isolate. So start with the cheese bath. You take your curd, you get your whey as a waste product. If you run it through ultrafiltration, your proteins and also fat, phospholipids, they're all here, retentate, and then your permeate mostly have lactose and some protein escapes through these membranes. So you get, that's a byproduct of whey protein concentrate production. Then here, depending on how many times you run it and depending on the size of the ultrafiltration membrane that you use, you get whey protein concentrate 34 all the way to 80. That number designates the concentration of the protein. So it can be as low as 34% protein, as high as 80% protein. And that's it, that's the limit. If I want to generate an isolate, so you run it through microfiltration. So what happens, the protein passes through, the protein is your permeate, and phospholipids and aggregated protein stay in the retentive. You don't want that, it goes to a different byproduct. And then you permeate, you spray dry and you get your protein isolate above 90% protein. So that is what happens to produce whey protein concentrate and whey protein isolate. Chromatography is used as well to separate based on size. So size exclusion chromatography. So here, you pack your column with particles that have different pore sizes. And your small molecules will pass in all the different pore sizes and the large molecules won't. So it separates based on size with the largest molecules coming out first and the smallest molecules coming out last. That's why we call it also gel filtration. So it's called size exclusion or gel permeation or gel filtration. They all mean the same thing because we're filtering based on size. So again, here are your particles, and each particle have different pore sizes. The small ones will pass through all the pore sizes and retain longer on the column, and the large one will not pass through and will elute. So basically, you use the elution volumes and the void volume and the elution volume, the void volume, and the total volume to calculate the constant. You plot that constant against the log molecular weight, then you can estimate the molecular weight of your different compounds, if you understand. I'm going fast here because these are things that you should go back and review if you forgot. Okay, let's answer here. Okay, to separate protein X. So this protein has a 90 kilodalton molecular weight, has a +5 net charge at pH 7. And we want to separate it from protein Y. They're different in molecular weight, they have the same charge. That's something funny about the proteins. Multiple proteins have the same net charge or similar net charge at the same pH. Multiple proteins have the same size. So we often, to separate different proteins, we use 2D and 3D chromatography. Okay. And then your protein Z has same molecular weight as the first one, but only +2 net negative charge at pH 7. So what do you do to separate? A and C. What's that? Trying to remember that question from before.
What?
You're trying to remember that question from before, aren't you? Yeah, all three of them. So we really don't care when we want to do two-dimensional chromatography. We don't care if we start with size exclusion and cation. You start with either one. The first one, if you go here, you're going to separate the +2 from the 2 other proteins. And then you separate the 2 other proteins by size exclusion. If we go with size exclusion first, I'm going to get these 2 proteins separated from that. And then if I do ion exchange, then I will separate them based on their net charge. Okay. Now this one in the middle, also I can precipitate this with some salt. I keep these 2 in solution. And then I can use membrane cutoff of 40 kilodalton and then separate them that way. Often it's not that easy, but you get the concept. It's not that easy. You have 100 different proteins at a time, and this is an actual procedure I did as a postdoc to get to an enzyme inhibitor. Look at this annoying process. Probably it was like 3-4 days of work. where you start with milk, and I want to get one enzyme inhibitor from starting off with milk. You go get the milk literally from the cow, from the. You start there.
Did you milk the cows here?
Huh?
Did you have to milk the cows?
Not me, the students, but I got, I got them. So, yeah, because we want it fresh, and then the first thing we do defat. And then you get, you centrifuge at only 4,000 G, you get the fat layer on top, you get the somatic cells in the bottom, and then you have everything else in the middle. All right, so I do also centrifugation. I get precipitate the casein from the whey. I don't want the whey. I know my enzyme inhibitor is in the casein portion, so throw away the whey. And then we resuspend. I'm not gonna go over all the steps, but what you can see here, pH, centrifugation, salt, remove supernatant, adjust pH, dialyze, adjust the pH, the salt, dialyze, on and on and on and on, and then you get your final. Yeah, because it's not always as simple to protein susceptible. So. Hey. The fun stuff. Oh, that was not fun as much as this. Okay, so you do have answers to these questions? Yes, we do. Why did I post online? What's that?
I thought I didn't have the answer, but I can see them. Yeah.
All right, then. I'm not gonna ask them anymore. All right, here we go. So protein characterization, you have the structural here with like looking at the amino acid composition, the sequence, looking at molecular interaction, molecular size, surface properties. So we do all of that to characterize the structure, but we also characterize the protein in terms of functionality. Functional properties can be biological, can be physical, okay? So if it's an enzyme, we're measuring enzyme activity, for example. Physical, dilation, emulsification, solubility, forming, etc. Or it can be immunoreactivity for biological. So enzyme activity, immunoactivity, antihypertensive activity. So these are considered functional properties by biology. Denaturation is also structural. So we have the structural characterization, we have the functional in terms of biological and physical. So methods, oh my gosh, we have an infinite amount of methods that we can use to obtain a lot of this information. So the structure is impacted by a lot, by intrinsic factor and processing. So when we determine protein structure, we're really looking at, with the protein configuration change, the nature, the open, secondary structure change, tertiary structure change, new molecular covalent interaction happen. So we try to study that. We look at molecular weight distribution. We look at, did it get smaller, did it get large polymers, did it form dimer, did it form very large aggregate, and then we look at molecular association. Are the molecules interacting by non-covalent interactions? Are they interacting by disulfide linkages? Did we form a glycation bond? What happened? So we look at molecular association and type of interaction. And we look at surface properties as well. So a lot of different things we study as impacted by processing. So what I want to spend the last few minutes with you is giving you examples as to when it is and why we do structural characteristics or analysis. So food is processed. So proteins are processed. Protein beverages are processed, right? Let's take a protein beverage as an example. So you want to put a high protein beverage, you want to formulate it, you want to keep it on the shelf for 6 weeks. The longer it is, the better it is for the industry from economical perspective. But you want to put a lot of protein in there to claim a high protein source. But each protein have different denaturation temperature, different molecular characterization. So we want to determine the impact of the thermal treatment on the protein characteristics to be able to understand I can put 5% protein, I can put 3% protein, I can put 10% protein. This is going to be shelf stable for 3 weeks, it's going to be shelf stable for 6 months. This is going to be shake and drink. This is going to be shake, shake, and really shake and drink. And or this is going to be a clear solution over six weeks of storage. So that's an example of, you know, when you denature, you change the structure, you increase the specificity, you increase the polymerization, and that's going to cause limitation on how much protein you can include, and also the shelf life. So linking the structure to functionality to the impact of thermal processing. All right, in this example here, valorization, increasing the value of side stream. One of the, or two examples, who can give me an example of a very popular, or a couple of popular ingredients that were serendipity valorization kind of thing? Or you? Right, yeah,
What, like it's an oil seed, so it was used as a rhino for oil, and then like we discovered soy protein isolated some high in functionality.
We discovered soy protein meal that used to go to animals after pressing the oil out. So the oil was used just for like industrial oil even at some point, and then we discovered the value of soy protein about 60, 70 years ago. What another example? Whey protein. See, you got it. You got it. Yes, whey protein is the most expensive protein ingredient, the most desirable from a color, flavor, solubility. It's one of the expensive protein ingredients, and it was used to be thrown away. You make the cheese, you take it away, you throw it out, you know, waste problems, biological problems, but now we have like.
I have a question. So is it true? I heard that like whey is more expensive than cheese now. So
Yeah, it's very expensive, really expensive. Because it not only have really good high nutritional value, it's very yeah, it is. So that's a successful valorization story. You go from a waste product to throwing away, generating biological kind of like issue with throwing away these organic material, and also, you know, tons and tons and tons of whey get rid of, and suddenly it became discovered, oh, wait a second, there's protein in it. Oh, wait a second, it's very nutritious. Oh, look at it, it's very soluble. Now, what we're trying to do is similar thing with others. We're not as successful. But we're trying to see, okay, look, there's sunflower. Can we utilize the meal like we utilize the soybean, sunflower, canola, okay, potato protein. They produce starch, and then they have this all that water, and it has very little protein, but they're trying to produce protein ingredients. And actually in Europe, they have a market for potato protein, but here it's not going to fly because you don't have that much production, and you need tons and tons of protein ingredients. Where are you going to get? How many potatoes are you going to use? So, look, valorization. So looking at those byproducts and search for structural and functional characteristics to kind of transfer low income, low value byproduct into a high value source of ingredients. Yeah, of course, protein separation, especially with those with plant protein business. All these plant proteins, they have different characteristics. Some do not solubilize at pH 7 or 8. That wishful thinking. Some require like pH 12 to be solubilized. So there's so many different proteins with different ways to get them out of their matrix. So we want to understand all of these different ways that we want to try to get that protein out. How does it impact the structure? How would that impact functionality? So, and then we try to devise isolation processes that have the least impact on structure and functionality. Okay, so competitors, that's kind of everything we do in industry. And we've gotten this big project, PepsiCo is like, they don't care about competitors, but they wanted to know how those different ingredients differ and how can we utilize them? How do they differ in structure? How do they differ in functionality? Well, in a CPG company, they just want to understand so that they can select the source of the ingredient. But for ADM and the Cargills and the ingredients part of the world is like, how can we make our pea protein better than this other one? So change in functionality. Sometimes we have new equipment. Sometimes we have different milling technique. A big example we had with a company of late state milling. So they were trying different milling techniques. And they wanted us to see how does that impact protein extractability. So they gave us a lot of different samples with different particle size. And also we noticed that when you have much finer particle size, that means it went through intense milling with some thermal impact. So you have higher temperature generated from excessive milling to produce those fine flour particles that impacts the protein itself. So changing the milling, working on technologies like putting in a new cooker to cook soy flour that is going to be used for microbial growth fermentation. And at Cargill, when I was doing the sabbatical, there was complaints that the growth of the bacteria changed in their source with changing the source of the ingredient. And Cargill said, what did we do? Oh, we bought a new cooker. Okay, let's take batches from the new cooker and batches from the old cooker and see how that impacted the protein to see why the microbe is not able to digest the protein anymore. So that was an interesting example. And everything we do with the plant protein, they suck at functionality, right? So trying to make them like whey protein, is that even possible? Sometimes, depending on how we do it. So we do modifications that we want to try to make it industrially feasible. And then we try to see what happens to the structure and how that impacted enhancement and functionality. The last one here, for I said to Paul.
I think you want one to play.
What?
I think you want one to play.
Did I?
Go back.
Oh, I did go on to many. Yeah, and then also looking at interactions of the protein with different components, because proteins don't exist in the void. So you have water interaction, fat, carbohydrate, salt interaction, what different bonds happen and how does that impact the final matrix of the food. So it's very, very important to do structured characterization. And next time I will continue with how do we do structured characterization. Okay, so Zoom, be prepared, dress up nicely, and brush your hair, brush your teeth, and I will see you in person with all the videos on, not in person, on Zoom.